This is Y, and I'm a student currently in a sem break and is bored out of hell. So I've decided to make a simple video on the magnitude comparator, which is a very simple circuit designed to compare the value of two input numbers and output whether if they are equal, one is bigger than the other, or vice versa. If you came across this video, it's probably because you are searching for magnitude comparator or something like that. And I hope you have basic knowledge on logic gates, Carnot maps, and some patience. Alright, where do we even start? What's a magnitude comparator? A magnitude comparator is a circuit that takes in inputs and compare. So, no matter what the input is, we always have three outputs, and only one of these outputs will be valid at one time. The number of input depends on what kind of number we are comparing. So, in the basic part, both the inputs should have the same size so that the circuit is not complicated. Then, the total number of inputs is both of these inputs added together. Let's say we are comparing two 5-bit numbers expressed in binary form. Then we'll have a total of 10 inputs with 5 inputs representing each number in binary form. So, in this, with each of these representing one digit, you know that this one here is the most significant bit, right? In comparing these two numbers, you want to start with the most significant bit. This is because the most significant bit alone is enough to counter every bit to its right. You see that this number is larger than this number with only one here. So, the number of outputs we have said, there are 3 outputs. And let's build a output map. And we have 4 combinations here. Let's say that this is A4 and B4, the most significant bits from these two numbers. When A is equal to B, we know that either they are both 0 or they are both 1s. So, the output is this. And when A is larger than B, there's only one case here. So, there's only one here. And it's the same thing for A is smaller than B. And now we can build a Carnot map. For A is equal to B, we have 1 in these both places. And to obtain the SOP expression, A0 B0 plus AB. It is very simple as to how You don't need a Carnot map to determine the expression for both of these cases. In A is larger than B, you can see that it is A and B naught. So the expression is simply A and B naught. The same thing applies. So you have now these three expressions for the three outputs for the bits of A4 and B4. Let's say we take this and see what it looks like. This is very similar to a pattern we have seen before in a logic gate called the not exclusive OR logic. And if we try to negate the exclusive OR logic with some simple Boolean algebra, this is using the Morgan's law, and the Morgan's law again on this step. And we know that A double complement is equal to A. Finally, and an expression dot product by its complement is equals to 0. Hence, and this is the same thing as what we got here. So what is this? We have complemented the XOR logic. So this is the exclusive not OR logic. Alright, so we need a method to design the circuit for this exclusive not OR logic. Of course, this is preferable, but we want a unit of this circuit at the same time to give us this, and this. So obviously we need to start from this expression, right? Because we have the A smaller than B, A larger than B, and the whole thing is representing if A is equals to B. So if we start from this equation, it should be something like this. Alright, we can see that this is A and B naught, this is A naught and B, and this is the X and OR logic we wanted, which representing A equals to B. And you can see that we can get the logical expression for all three cases at the same time with this unit of design. But note that we are using a total of 6 gates here. In a digital logic circuit, the gates are where the power loss is occurring. So it is preferable if we design the gate with, we design the logical circuit with lesser gates. Let's tune this design a little bit. Let's use the XNOR logic gate. So this is a total of 5 gates, and this is the expression. A B naught is for this and for this. So this is using only 5 gates. Alright, so this is one unit to compare between a single bit. We are comparing A4 and B4. So for a total of 5 sets of comparing, we need 5 units of this thing. Now let's devise the equation needed. For the output of A equals to B, actually this is all indexed with 4, the single bit comparison. For the whole number to be equal to each other, what you need is that you need all 5 units to be outputting 1 at this place, right? So let X4 denote that A4 is equals to B4. Then for A to be equal to B, you need X4 multiplied by X3, X2, X1 and X0, and they all need to be 1 in order for this result to be 1. If either of them is 0, meaning that one of the pair of bits is not equal, this thing will be 0, right? So that's what we want for this equation to do. What if we are taking A is larger than B? How do we get the equation? When we want A is larger than B, we know that we need A B naught, but not just any A B naught. We need each pair of them. Every pair matters. Now you have noticed why is there some empty spaces here. That's because if this is equals to 1, meaning that A is indeed larger than B at the 4th index, what happens to the other indexes if they are equal or if they are unequal? If after the 4th index there is still equal indexes, they should be 1 also, right? But 1 plus 1 equals to 1, 0. And you'll get the result of 0. That's not what we wanted, right? So we know that when this expression is outputting 1, this expression will be outputting 0, right? And to make a expression to go to 0, we only need to multiply the 4th XNOR logic output here, 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 and here. So in case if this results in 1, all of these will be multiplied by 0 so that it will not affect this expression. The same law applies to the third place, the third index. The same thing goes to the second index and the first index, and nothing else, because there's nothing here, so the equation can stop here. So this is the expression we want for A is larger than B. What about A is smaller than B? You just change everything here to A, not B. The other things still stays the same. Alright, once we get this expression done, we can start to design the circuit. And we can see that this is simply taking one of the AND gate output of the XNOR unit and 4 XNOR outputs from the other 4 units, right? Alright, here we have the logic of A equals to B. And we can see that if we change, the output will be 0 here. Next, we will start building on the circuit for A is larger than B. We are using 5 AND gates and 1 OR gate to complete this output. Alright, now it is completed. Just now I made a little mistake of connecting the wiring to here, in the middle part here, where there are no input ports. I've changed that, but the connection is still the same. You can see that the connection is taken from here, the XNOR logic outputs, to here with each of the A and B not terms. And finally, add all the terms together from here, and you got the A is bigger than B expression. Let's try it out. See? It turns to 1 instantly. Whenever A is larger than B, we will activate this output. it is done for A is smaller than B. Let us try out and see if there is any mistakes. We can see that A is indeed smaller than B in this input. And A is still smaller than B in this input. And we can see this is a perfectly working magnitude comparator for this circuit. And in this part, it is very simple. You just need to exchange the NOT gate input of A and B, because their only difference is that this is using A and B NOT, while this here, the bottom part, it is using A NOT and B. And they are the same for using the OR gate to add up all these outputs from the individual AND gates. And if it's required that the circuit is to be designed closer to what will be represented in real life, because in real life there were no commercially used 5 input OR gates, so you will like to compile them with two different OR gates, one to sum up either 4 of them, and one to sum up the first OR gate and the last input when the 5 input gate is not available. The same thing applies for 6 inputs. For example, this here. Since you can change the number of inputs in this software, it's very convenient. So this is a simple model of 5-bit comparator. And this is a model of 6-bit comparator based on the same working principle. You can see the input is indexed to be 0, 1, 2, 3, 4, 5, a total of 6 bits from each number, and a total of 12 different inputs. And basically, this is all to design a working magnitude comparator in using Logisim. It's a free software. You can download it online. So this concludes our design of the circuit for magnitude comparator. If you have any questions, feel free to comment your question below. I will try to answer it. And good luck in your studies. Thank you very much.